I'm talking about the awful lieutenant I have. That you shouldn't.
Okay, now it's time for the awful instructor you have, so. Okay, today we're going to be flipping a little bit between looking at some event graph type of stuff and some of the SimKit implementations, and hopefully that will make a little bit of a stronger connection between the two. So the first thing I want to talk about is extending this model that we had where we had servers with different efficiencies. That is, in contrast to our basic multiple server queue model in which all of the servers were homogeneous. And again, it's important to remember that in that context, homogeneous doesn't mean that they literally have the same service times. It typically means that they have the same probability distribution of service times, but they all have the same ones. And then in our system, if we notice that some servers are faster than others and some are slower. So the way that we were modeling that, in fact, let's see, yeah, there. The way that we were modeling that was to have each customer carry around their service time as an entity, as an attribute of their entity. And then in addition to that, each server carrying around what we're calling the efficiency as an attribute. So we have two different classes here. One for the customers, and we're going to have a whole bunch of those, and the other for the servers, in which we're just going to have a fixed number of those. And the way that that works with the way that the event graph goes is that when it comes time for the server to begin processing a customer, what the server does is the customer carries around their service time, which you can think of as the amount of work that has to be done on that. And the server efficiency is how fast the server can be working on that. So you see that we're delving into just a slightly more detailed representation of what this is about, and it captures the fact that there are quantitative differences between the two different servers. But then that also raises the question of how do you choose the next server? And now we've seen at least one other example of that in which we had two different types of servers and the customers liked one over the other. In this model, we were modeling the container of the server entities as a first in, first out, or basically that produces a round robin like effect. In other words, when a server finishes and they go to the end of the list, and then any server who hasn't been processing who's been idle the longest is going to be the next one to be served. That's implicitly how having a first in, first out container for the servers works. Okay, so that's how that model was operating. But what we're looking at is a situation in which, what if we had a different rule? So instead of the round robin, what if we liked the faster one? What if somehow we knew which of these servers was faster? In a machine shop context, you generally know which machines are faster than others. So and even if you have, in many situations, even if you have machines that are of the same make, a lot of times there are differences where one might be faster than the other. So how can we do that, given that our basic model used the first in, first out? Well, if you remember, last last quarter. We talked about writing custom comparators for situations where we wanted to change the criteria by which we sorted objects in a sorted container, right? Remember that? I know everybody does a core dump the day after the final, but there are some things you need to remember. So, yeah, so basically, now the thing is, this is where having state variables that are protected becomes important. Because if we locked our state variables down as private, then we don't really have access to them if we wanted to subclass. So if that were the case, then you have to basically rewrite the whole thing. But instead, kind of recap this a little bit, I expanded the little run method there. So here we have, so this is the entity, and this is how we subclass the entity, but so our queue, I called it queue with server efficiencies. Coming up with names is something just a little challenging. And so if you remember, the parameter now, instead of just the number of servers, we're going to have an array of all the servers. So whoever instantiates this is going to be responsible for creating those servers, assigning them their efficiencies, and then stuffing them into an array, and then putting it here. So here's the available servers are now in a sorted set, and the way that the entity comparator is based upon the timestamp. That's why we have to timestamp an entity before we put it on a sorted container with the default going on. So when we run that, let's just kind of so here's sort of the main piece that was implementing this. So everything here is pretty much almost the same as what we've seen before, except for this delay between start service and end service. That's how long it's going to take to process this customer using this server. And it's the product of the service time or the processing time from the customer and the efficiency of the server. So because this is a time delay, and again, remember that the wait delays are the scheduling edge. We call it a delay because it's the time, it's not the absolute time, it's the relative time between now and when it finishes. So if we start serving this guy now, this is when it will end. And it's the product that's due. So if you have a smaller efficiency, less than 1, say, then it will process it faster. And if it has an efficiency greater than 1, it'll process it slower than otherwise. So the same customer with the same amount of work is going to take a different amount of time depending on which server they get. Okay, so it should be clear that that's a bit more complicated, a little more detailed, and hopefully a little bit more accurate in the way that it's representing what's going on. And we can ask questions of this model we can't ask of the other model, such as what would be the impact if say, through training or upgrading, we increase the efficiency of certain of our laggards or our slower servers. The other thing to remember here, too, is that notice that in this case, the end service event has both a customer and a server as its argument. So we have 2 arguments. So we've seen events with no arguments. We've seen events with 1 argument. Now we've seen an event with 2 arguments. And the sort of the English description of this is completion of service on this customer using this server. So you need both of those. You need to know which customer it is in order, just only in order to compute the time in the system. So if you don't know which customer finished service, you don't know how much time they spent in the system. We could actually do away with that and still have a model that works roughly the same. It's just we won't be able to get that particular measure. But we do absolutely have to have the end service event with the argument of the server, because we need to know which server to put back in. If we just say there was an end service, the next question is on which server. That wasn't an issue in the previous models where we were just counting because we didn't care. We just said, well, we have one more server. We'll just increment the number of available ones. Okay, so now how is that implemented? Well, the two arguments are simply implemented as arguments on the method that corresponds with the end service. So the end service had two arguments, and one was a server, one was a customer, and there are the arguments. So now when you schedule that, you need to pass it the two arguments. In this case, since we're scheduling an event that requires two arguments, we're going to pass it the two ones that correspond with that. And the difference between scheduling an event and invoking a method are that the compiler doesn't help us. If we were to forget one of these arguments, there would be no error, no complaint, but it just wouldn't work the way we would expect. That's why running it in verbose, if we ran it in verbose mode, we see, well, wait a minute, a start service event occurred with a server that was available. It scheduled the end service, and we would actually see the end service event appear on the event list, but none of these state transitions would occur. Why? Because we weren't matching the arguments. Okay, so when we run this, so here I'm running it with three servers. One that's sort of, quote, normal with an efficiency of one that's sort of speedy, and one that's clunky. And so, we get a certain average number in the queue. We can have delay in queue. Again, we can just, and then we look at our utilization. So we can actually, in this case, we were computing three utilizations. Now for these, because we are firing, we're firing two types of property changes. One is for the available servers, but then when a server gets busy, what we're doing is we're firing an index property change with its ID. And every entity has a unique ID. And so in this, well, let's see, let's go back. Yeah, so here we're looking at the busy. If you remember, there are kind of two ways to think of a server. Here we're actually doing it both ways. So for the individual server entities, we're saying, okay, we're going to give you a 1 when you're busy and a 0 when you're not busy. And these are index property changes, and the index is the ID of the server. And so what's happening here is we are listening to that with a multiple simple stats time varying object. And what that does is the multiple modifier, if you will, what that does is that listens for index property change events and sorts them or keeps them separate by the index that it hears. So when you're firing an index property change event where the index is the index of the server, then this stat object will keep track of the time varying average, or the time varying stats for that server. And we can get it. Now these multiple guys, in addition to the regular getters for mean, variance, and etc., have getters where you give it the ID. And if it has that ID, it will return it. So here what we're saying is get the mean for this server's ID. And the thing is that in this particular case, notice that the IDs actually went 1, 2, and 3 rather than 0, 1, and 2, which we would expect and why? Because the ID of a server is just unique, and it comes from the entity's unique ID. So it can be whatever. So in this particular case, we can compute the average overall utilization, but in this particular case, when we see the utilizations for the individual servers, we see a certain correlation between their efficiency and their utilization. In other words, and it's intuitively what you would expect, although the magnitude isn't something that you can necessarily predict. So the server 1 is the clunky one, that's the slow one. And that has a higher utilization. So intuitively, for the round robin thing, I mean, each of them basically is getting roughly the same shot at processing customers. But this has a higher utilization in part because it spends more time. For every customer with a given amount of service time, it's spending more, almost 50% more time than this one, which just spends the normal time. And then server number 2 has a smaller efficiency. That's the zippy one that, if you notice, it has the lowest utilization, which means that it's processing them and getting out of there. Okay, so now, what if we wanted to take our model though and say what would happen if instead of just a round robin, what if we said I like the fastest one? So if in this case, and if we look at it, basically we're removing the first customer. So who's the first customer? In this case, it's the first one based on the timestamp. And notice, we're stamping the time before we put it back on the available servers, and that means that it's going to be in order of the ones that were put in, earliest. That makes it a first in, first out. But what if instead of removing them in that round robin way, we wanted the fastest one? So this doesn't do that. So how can we do that? Well, and how can we do that in the laziest possible way? So laziness in an object-oriented world generally implies some kind of subclassing. So how can we subclass this and not have to rewrite a whole bunch of code? So here's how we do it. And basically, it's almost no code at all except for our comparator. So what we're going to do is we're going to write, and in this case, I'm going to write it as an inner class for this one. I could have written it as a separate class, 6 of one, half dozen of the other. I noticed that they're getting a lot of classes here. The one downside of Java's convention that there's one class per file is that you start to get a whole bunch of files, which is then why organizing your projects by packages becomes a little more important. So, but we're not really doing that here. We're just kind of doing this stuff. So doing it as an inner class, and I'm making it private because this is the only thing that's going to really use this. Although if if this were something that I was going to reuse a lot, then I would actually put it in a separate class. So we're going to write this comparator. And so a couple things. First, if you remember, if we're comparing exactly the same things, then we want to return 0 and kind of end a little early. And then now here's the thing, because the efficiencies are doubles, we can't just subtract. If they were integers or something like that, we knew that they were all going to be different, we could subtract them, but you got to be a little careful with that. So here instead, we'll kind of just do it the old-fashioned way and just say, if the first one's efficiency is less than the second one, then we're going to return -1, which means it goes first. Otherwise, if it's greater than, we're going to return 1, which means it goes after. And then otherwise, now, we could have two servers that were distinct with the same efficiency. If we didn't have this last piece, do you see what would happen? We would be in a situation where no two servers could have exactly the same efficiency. And that's not a reasonable thing. So if we get through all of these, in other words, if by some chance there's an exact equal, then we're just going to use the default comparator. Okay, so now we have a way of having our available servers contain, at least in theory, our available servers container can now sort the servers based upon this criteria. In other words, have the fastest one first. So if you show up and there's more than one, I get to pick the fastest. Okay, so that. Now, how can I? But this in and of itself isn't going to do it. I have to actually put it into the event graph piece itself. So how can I do that? Well, it turns out I don't have to do a whole lot. Okay, first of all, I'm going to subclass what I'm calling Q with server efficiencies. That's this basic model that we already had. And I'm calling this the fastest servers first Q. So the first thing, again, because constructors don't get overloaded, we have to write constructors for these. Again, so we have a master constructor, which is just going to have our array of all the servers. We're going to have a 0-argument constructor still. And then, but what we're going to do is, we could have done this in a couple of places, but I chose to do it in the reset method. This is slightly less efficient than doing it in the constructors, but it's a little more. The thing about the reset method is that gives you a chance to really hijack what's going on, regardless of what happened in the constructors. Because the thing with this, and we're going to get to this in a few weeks, about the reset method. Why this reset method? You may have been wondering, or maybe not. I don't know. Maybe you don't care. That's okay. No reason to care at this point. But what the reset method about is this, and you can just sort of think, put this away for when we start doing it. We've been running our models one time. And in these models, we've been using random variates. And then we've been doing things like estimating utilizations and average number and average delay, et cetera, like that, using one replication. Now, in the world of using simulation for analysis, that is a mortal sin. Because, and here's the way to think about it. Oh, darn, I don't have it. Supposing I had a coin and I wanted to know whether or not it was fair. How would you decide? So I got a coin. Maybe it's a weighted coin. Maybe it's say, well, a coin. 50-50 heads, tails. Well, how do you really know? You flip it, okay.
See what happens.
Right, so oh, wait, here's a coin. So I got a coin. Okay, I don't know if this is fair or not.
Is it a quarter, sir?
It's a dime. Sorry.
I need quarters for laundry.
Yeah,
Every week. I
Yeah.
get excited about quarters.
Anyway, so
Anyway.
they don't take dimes, I guess. Okay, so,
Unfortunately, no.
all right, so I don't know if this is a fair coin or not. So I'm going to flip it one time, and it's a heads. All right, now tell me if it's a fair coin.
Yes.
Okay? Now, how confident are you that this is a fair coin?
Not at all.
Not at all. I mean, in fact, how much information do you know about the probability of heads with one flip?
That in the one time it was 100% probability that it was the whatever you just flipped.
Yeah. Well, the one thing you know is that it's not a two-tailed coin. That's because if it had two tails, then it would be a tails. That's the only thing you know. It's like that one that there's a sheep in Scotland that's black on one side. If you've heard that. That's it. Anyway, so running a stochastic simulation one time and trying to get any truly meaningful, valid results out of it is not a reasonable thing. That is simply not reasonable. So we need to run it many times, and we will be doing that. But here's the thing. These are just ordinary programs, and as a program, when this finishes, the state variables are whatever they are. So at the end of one of these replications, it's like there are so many in the queue and so many servers available and all that sort of stuff at the end of the replication. So if I want to do another replication and I don't do anything, then I'm starting that replication in a different state than when I started this one. And what that means is that it's not an identical replication because I'm changing the initial conditions. So how can I guarantee that my initial conditions are going to be exactly the same when I run another replication? And that's where the reset method comes in. Because the reset method initializes all of the state variables to their initial value, and when reset gets called, on the second replication, everything gets set back. It's like a giant reset button. Okay, so here, now, what is it that I mainly have to do? Well, okay, I'm calling the super reset method, and the super reset method does a whole bunch of stuff, but basically, in the super reset method, it was just basically clearing my containers, and I was relying on the init event to initialize the, where's my init event? My init event to initialize the available servers. So here's what I fire an index property change event. So the argument here is the index of the array of available servers. So all of that is happening, but so all I'm doing now is instead of clearing the one in the superclass, I'm actually overriding the one in the superclass and setting it to a new tree set with this comparator. And so that will just sort of override everything in the superclass at the reset. But then it will, as it adds the servers, it will then keep them sorted according to this comparator. And in terms of the component, that's all I have to do. So kind of given that I've written a very simple comparator, I basically have one extra line of code that will now allow me to implement this new feature. So let's, I want to save, let's just save these guys. And then now I'm going to run it under exactly the same conditions as the first one. So I got my 3 servers, the normal, the fast, and the slow, same other, and I'm running it once, and then sort of let's compare what we had here. So first we see that the average number in the queue has gone down a little bit. The average delay has again gone down by just a smidgen, but what's more interesting is that the utilization, now notice this, the utilization of the fast server now has gone way up. Now, is that intuitive? So why do you think that? And again, now keeping in mind that this is, we would have to run replications to have a statistically valid, but let's pretend for a moment that this is.
It prefers the faster one.
Yeah, in other words, every time you come in, that one gets picked more. So it's going to be busy more. I mean, that's kind of intuitive. Whereas the clunky one now, their utilization's way down. Why? Because they get picked last. They're just sort of sitting there. So in many situations where if there's an available server, it's going to be this guy. And then the normal one, let's see what happened with him. He was 8.85. He went down a little bit, just who knows. But again, these are the kinds of things that you can tease out of a model like this. And again, this is not a statistically valid one. Obviously, in order to have any valid conclusions, we would have to have something where there were more replications. Because we don't know. You don't know if, maybe this got lucky. Maybe this is just a random occurrence or not. Okay, so so that's how we can. Oops. That's how we can. Again, tweaking some things, and that's how. Tomorrow we'll look at some other examples where we can take something that we, take a component that we had already implemented and subclass it and tweak what we're doing with it. In some cases, in this case, we're just kind of tweaking a policy, but we can actually expand the model fairly easily. So tomorrow I'll show you how to take our simple server model and expand it to take batch arrivals. If you remember, there was that problem, that modeling problem where we said, okay, instead of just one guy showing up, what if we had a whole bunch of guys showing up? So that's a situation where, if you have a facility, then maybe a bus drives up and a bunch of people get off instead of just one. Okay, so let's. Now, we've touched on this, and I want to reinforce this idea for array state variables. And that is, in 99.9% of the time, whenever you have a state variable that's an array, there is typically only one element that changes at any given event. We've seen that in every case. I've seen that in almost every. I can't think of a single case where an entire array state variable was changed at once. The only, sometimes maybe if I'm initializing something and I sort of clear everything out, then that, there's that. But that's really more of an initialization than a true state transition. So the notification, like this fire property change. Now, the property change thing is something that it's built into Java. So one of the, we probably won't touch on this here, but because the property change thing is something that a lot of Java classes, in particular many GUI component-like things, can be responsive to listening for property change events, that enables us to kind of work easily with things like that, but we won't get into that too much. But again, the state notification is the property change event, and in this case, the fire property change is for scalar states, and the index property change is for indexed ones. And what the information that the property change event, the index property change event has is the name of the state, and we've seen things like queue and available servers and stuff like that. The index of the state, so it's like which of the indices have changed, the new value, which is kind of the critical one, and then there's an optional old value. We've used old value, new value. That also comes from what Java does. Java likes to kind of do that. So we kind of go along with that to a certain extent. Okay. So let's look at a simple example of this. So supposing we wanted n arrival process-like events, each with their own intra-arrival times. In other words, every time we've been using the arrival process produces a stream, a sequence of arrival events, but with no argument. Sometimes we want an arrival event with an argument, and if you remember in the transfer line, we wanted one with just 0 as its argument. But sometimes we want to have a situation where we have more than one, each with their own argument. And we've seen one example of a component like that, at least in the abstract. So in this case, we have sort of a certain number of these processes, and by process, I mean arrival process-like things. Each one is going to need its own inter-arrival time, so T sub A I, not a capital I, which is something else, but a little I, is the inter-arrival time of the ith arrival process, and so our state is also indexed by we're going to count the number of arrivals in the ith arrival process. Each one is going to initially be 0, and the index is going to go 0 through n minus 1, keeping this 0-based argument stuff that Java inherited from C, and all modern languages have that issue. Okay, so here's a component I'm calling a multi-arrival process, and as you can see, it combines our for loop with our arrival process-like thing. So again, like one of the things to remember is the difference between an arrival process pattern and a for loop pattern. So what's the difference? Yeah, the main difference is the inter-arrival time between the arrival process pattern has a typically positive delay between the next arrival. The for loop pattern has 0 delay. In other words, the for loop pattern will occur immediately. The for loop pattern always has an argument. In this case, the arrival process pattern happens to have an argument, but the key difference, they kind of look the same. They both have a self-scheduling edge, one self-scheduling edge. The difference is the for loop pattern has a 0 delay, and the arrival process pattern has a specific time delay. That's the difference. So the init event will all happen, the main use case for the init, for the for loop here, is that we're initializing a state, an array state variable. That's the main one. The argument is going to be the index of the array state that we're initializing, and we schedule the next one immediately. And in practice, it isn't always necessary In this, it isn't strictly necessary, but just as a common practice, I will use a high priority just to guarantee that these all happen before anything else. So in the implementation, we have this, instead of fire property change, we have fire index property change. And let's look at an example. Now in this case, okay, so this is our is this the one? Yes, yeah. Multi-arrival process. Now, when you're looking to subclass things, what you want to do is you want to look for common arguments in the that we might want to subclass. So we've seen a lot of examples where we're subclassing the arrival process and kind of adding some additional types of things. In this particular case, it's not something that we can really easily do. And so in this case, there's really nothing to be gained from subclassing arrival process. Now we could take a different approach and actually kind of have a class that has a bunch of arrival processes as its parameter, and that would be another interesting type of thing. But we're not going to go there for this. We're just going to take the most basic approach, which is we have a single parameter, which is now an array of random variables that are the inter-arrival time generator, and an array of states, which are the number of arrivals for each one. So our master constructor we give it this array of inter-arrival times. We call the setter. Again, we have a zero argument constructor for reasons that we haven't gotten to yet. Now here's the thing, is that when we have objects as if we have objects as our parameters, then we can usually use the setters to handle that, because you see, to instantiate one of these, whoever is instantiating it needs to create this array of inter-arrival time generators. And then when I set it, again, now all of our, where was it? Come on. Yeah. Since this is an array, remember we always use clone. Oops, and we should use clone here too. Oops, Chloe, clone. Okay, so for these setters and getters, always clone. That rule hasn't changed. But we will typically need to instantiate our state variable somewhere. Here's the dilemma. The dilemma is we don't know how big to make this array until you tell me what the inter-arrival time generator array is. In other words, I need to know the size of the inter-arrival time generator to know how many of these I'm going to make. Now there are a couple of ways to do this. I mean, I could have instantiated it in the setter. Oops. I could have instantiated in the setter, but you generally don't want to do that, at least not all the time. So instead, I did the same thing here, I did it in the reset method. So the thing is, before the simulation kicks off, I need to make sure that this array has been instantiated somewhere. And the thing is, because I don't know how big to make it, I just need to know what this array is and how big it is, and before I do this. And then this has the additional okay, so just every time I run it, I'm going to have to instantiate a new array. you think, well, ideally that's not recycling as much as one would like, but just okay. So and then we're going to spin the inits again, just like we have our init. We schedule our first init from run, passing it as 0. Here we're firing the index property change of the index that we just had after having set that one index, in this case, to 0. And then here's the self-scheduling edge for the for loop. And then here's the scheduling for the arrival process like one for that integer I. And then what does the arrival event for int I do? Well, again, we fire the index property change for that particular number of arrivals index, and then schedule the next one. All right, so tell me. Okay. Okay. I have time to just sort of test it, just to kind of see what's happening. So let's create an array of random variates. I'll have 2 exponentials and a uniform instantiated with the master constructor. Here again, the simple property dumper is smart enough to know when it hears an index property change event. And then here, I don't know if we've talked about this, but now normally, see, if I don't do anything, this is just going to kind of keep going forever, and I'm going to have to red X it out. We've seen stop at time, and that's fairly intuitive. We say it's going to run for a certain amount of time and then stop. But there's another way to stop the simulation, and that is to say after a certain number of events. And in this case, I want 10 events of arrival, but now if I leave this out, then it's going to run forever, because that will mean a 0 argument arrival event, and we don't have any with this. So what I have to do is I have to tell you what is the class of the arguments of the event that I want to count. And now in this case, notice that the event itself had a primitive argument, but even if there's a primitive, we always have to give it the object wrapper. So if my argument is an int, I have to say the integer class, not the int class. So if I run this in verbose mode, then we can at least see what's going on. So again, if I just print, hopefully you've seen by now, if I print a sim entity-based component, it will list all of the parameters and what their values are. So this tells me whether or not my arguments actually made it in, because it's just too easy for that to fail. Okay, so here's my run event, and here's my init event. So number of arrivals for 0 is 0. Number of arrivals for 1 is 0. Number of arrivals for 2 is 0. Okay, now the thing is actually kind of running. So now notice that whenever there's an event scheduled with an argument, the value of that argument is in curly braces. So here we've scheduled an arrival with index 0, an arrival with index 1, and an arrival with index 2. And notice that the arrival with index 0 was scheduled first, but it's going to occur second. Why? Because its delay was greater than the 1 for 1. So that's the event list sorting things according to the earliest event. So now arrival 1 happens, and so the number of arrivals for 1 goes from 0 to 1. and arrival 0, so what we're doing is we're just verifying that we're getting the right state transitions for the right states. Okay, so just in one last thing, which I'll pick up tomorrow, like how can we use that? Well, do you remember this a situation where we had two types of customers and only one type of server, but two types of customers with an argument? So if I create one of these multiple multi-arrival processes with n equal 2, that will produce arrival events with an argument of 0 and an argument of 1. And that will then, they will get heard by a component which requires arrival events of either 0 or 1, and that will drive this whole thing. So tomorrow I'll show you the implementation of that.